So to understand or begin to understand quantum mechanics, we first have to take a trip into physics and make sure that we understand light. So light is a form of electromagnetic radiation. So electromagnetic radiation has an electric field and a magnetic field. And these take the shape of oscillating waves, and they're perpendicular to each other. So the magnetic field will oscillate, say, up and down, and the electric field will oscillate horizontally. But they travel through space together. Electric field is a region in which electrically charged particles are going to experience a force, like an ion would experience a force within an electric field. A magnetic field is where a magnetized particle will experience a force. So, important thing about electromagnetic radiation is it all travels at the same speed. Light is electromagnetic radiation. It's one form. Light travels at the speed of light. All electromagnetic radiation travels at the same speed, 3 × 10⁸ meters per second. This is really, really fast. Some of the old cartoons show this old guy, he's blowing out the candle, and then he jumps into bed, and then it gets dark. Is that possible? No. Because when you extinguish the candle and the light stops being generated, it's like dark instantly, right?
He'd have to be moving faster than light.
He'd have to be moving faster than the speed of light, which just is not possible.
Nothing to observe at that point.
You guys are getting into this a little too much.
We're going to use that to get out of a lot of things now.
So here is an illustration of electromagnetic radiation. So here we have electric field component, magnetic field component.
Do we need to know the speed of light?
You do not have to have the speed of light memorized, no. But it's one of those things that we tend to use and end up remembering. So here we have the electromagnetic radiation is traveling in this direction. The electric field is oscillating in one plane, and the magnetic field is oscillating in a perpendicular plane. So here's a picture of some lightning. And I think you've probably all observed that you see the lightning, and then later you hear it, right? And you probably learned as a kid that you can estimate how far away it is from you by counting the number of seconds between. That's because sound moves at a much slower speed than light does. The sound is moving at 340 meters per second, and the light is moving at 3 × 10⁸ meters per second. So we can actually count seconds and estimate the distance based on that. But all light, all electromagnetic radiation travels at the same speed.
Even fireworks, same thing.
Fireworks, yeah, you see the light and then you hear the sound. So waves have characteristics. One of them is the amplitude. That's how tall is the wave. That's the distance from the node to the crest or the node to the trough. Let's go back to the picture for a minute. This would be the node. So we see this is oscillating around this line, right? Above and below. So that would be a node, and this is a node, and that's a node. And so the amplitude is the distance in height here. How tall is the wave? And if you think about waves on a lake or on a river, ripples in the bathtub, ocean waves, they behave in some ways the same as electromagnetic radiation. And so that at least gives us a visual picture of what to look at. So the amplitude of an ocean wave is how tall is it? For light, that's a measure of the light intensity. So you can have a dim light or you can have a very bright light, right? The bright light is going to have a higher amplitude than the dim light. Another measure of waves is their wavelength. And this is given the symbol lambda. That's the Greek letter L, lambda. It's like an upside down Y. That's the measure of the distance from one crest to the next or between alternate nodes. Yeah, here we go. So here's the amplitude, and here's the wavelength. It's from the top of one to the top of the next. That's how long the wave is, the wavelength.
That's a cosine.
Yeah, you can do things with sine and cosine and stuff, but we're not going to. Another thing is the frequency. And the frequency is given the symbol, I believe that's mu. It's a V that's got a little bit of a curve in it. So frequency, that's not a V. V is used for velocity, lowercase v. Capital V is volume. So we got to be really particular with our variables here. But the frequency is the number of waves that pass a point in a given period of time. So imagine standing, you're maybe up to your knees at the beach, right? And the waves come crashing in, right? To measure the frequency of the waves, you would count how many waves hit you in a given period of time. Maybe you do it 5 minutes or something. So it's the number of waves divided by the unit of time. And it's often given as hertz. Hertz is the unit, and that's used in electricity. And so, you think about the, I'm blanking. What is the frequency of? 60 hertz, yes. 60 cycles per second. Because this is alternating current that's in the outlets. It alternates between positive and negative. And how fast does it alternate? It's 60 times per second. So 60 cycles per second, or sometimes just per second. Question?
This might not relate, but what about your heartbeat when you're taking that? Would it be electrical?
So your heartbeat, there is electricity involved in your heart beating. And if you look at the, like if you're hooked up to a monitor and you look up the spikes and stuff, you could measure frequency and amplitude of those waves. But that's a different kind of a wave. So the total energy of the wave is proportional to the amplitude and to the frequency. So think about standing at the beach. Well, if the waves are really big and they're hitting you, you're going to feel that energy from them, right? They get big enough, they're going to knock you over, right? And the frequency is also going to have a bearing on whether you can stand up there or not. If they're just pounding you, bang, bang, bang. Ocean waves don't come that fast, but that's going to knock you over. If you get one wave every 5 minutes, it's like, oh, this is nothing, right? So the frequency of the waves and how tall they are is what determines how much energy there is. Well, electromagnetic radiation is all traveling at the same speed. So the shorter the wavelength, the more frequently the waves are going to pass you. I have to draw some pictures here. So short wavelength, long wavelength. I'm trying to make the amplitude roughly the same. So here's a person. These waves are traveling at the same speed. How many crests is this person going to run into? 1, 2, 3, 4, 5, 6 in this illustration. And this person is going to see maybe 2.5 because they're traveling at the same speed. So the frequency is related to the wavelength. Right? Short wavelength, high frequency. Long wavelength, low frequency. So the frequency is equal to the speed. The speed of light is usually represented with a lowercase c, divided by the wavelength. All light travels at the same speed. All electromagnetic radiation travels at the same speed. So frequency and wavelength are inversely related. One is, if one's large, the other's small. And it's one of those things that's a little hard to keep straight, and I draw these little pictures in my head. Like, how does it go? Oh, yeah, okay. What we observe with visible light is that different wavelengths our bodies interpret as different colors. And that's a whole nother subject, is how do we observe this electromagnetic radiation and turn it into all the beautiful colors that we see, right? So we have receptors in our eyes that the light hits, and when the frequency tells our brains different things, and our brains interpret that as different colors. So longer wavelength is going to be more on the red end, yellow's sort of in the middle, and then blue light has a shorter wavelength. Shorter wavelength, higher frequency. So wavelength determines the color of the light. The amplitude gives us the brightness of the light, whether it's bright or dim.
It's even more fun to think that the colors you see is merely just the light being reflected, that the object
Yes.
is absorbing all other wavelengths of light.
Yeah. What we see as color is what is reflected by the object, and the other colors are absorbed. Which brings us to this slide. So in this photograph here, this girl is wearing a red shirt. We see this as red when the white light hits it. And white light is not really white, it's not opaque, right? But white light consists of all the frequencies. So the light from the sun has all the frequencies present in it. And when it hits this shirt, the red light is reflected and the other wavelengths are absorbed. And so the red light comes to our eyes and we see the shirt as being red. Yes?
Like, what makes a certain wavelength reflect?
What makes a certain wavelength reflect? It has to do with the chemical makeup of the substances in the shirt. And so how do you make a shirt not be a white shirt? Well, you dye it, right? Not dye it as in not eating, but you dye it. So dyes are generally organic compounds that you can just tweak their structure a little bit and you can cause them to change colors. But they have a makeup that causes them to reflect and absorb different colors of light, different wavelengths of light. And that's a whole science in and of itself. So you remember we did the titration with phenolphthalein, right? And it was colorless, and then we added sodium hydroxide, and when we got a whole bunch of sodium hydroxide, and there was this bright fuchsia color, right? It's the same compound. Before, it was reflecting all light, and now it's reflecting the pink and absorbing the rest. Small change in its chemical structure causes it to change colors. It's pretty cool. So the colors, red, orange, yellow, green, blue, indigo, violet, they always, if we pass white light through a prism, we see a rainbow, right? And in fact, I saw a rainbow yesterday. We've had some rain, thankfully. And the colors always separate in the same order. This is why a child may draw a picture of a rainbow and you look at it and you're like, there's something wrong with that rainbow. Because they're just putting colors in it, right? They didn't necessarily look at a rainbow and put the colors in the correct order. The colors are always in the same order because they get split by this prism according to their wavelengths. They interact with the glass in the prism and are reflected and diffracted more or less. And so it's always red, orange, yellow, green, blue, indigo, violet. So one way to remember that is Roy G. Biv, like some really strange name. Roy G. Biv. Yes, question?
Find out ultimately why the rainbows to show all the colors instead of just picking one.
Rainbows show all the colors because the light that generates them is from the sun. And the sunlight is white light and it contains all of the colors. And so there's nothing being absorbed, but the white light gets separated. And so we see the red and the green and the yellow separate from each other. And the little water droplets act as prisms. Yeah.
I can't really wrap my head around it. Like, so is it projecting off a sun ray or just this like brightness overall?
Well, so, you go outside and it's light, right? You can see. Do you see, like, beams of light coming down? No. Have you ever, my house has been rather dusty for the last couple decades, but you get a sunbeam streaming through the little window in the front door, and you can see the beam, right? And you look carefully, and there's little dust particles. The reason you can see the beam is because the dust particles are scattering the light. But when there's nothing large enough to scatter the light, you don't notice that there's sunlight streaming down, right? There's light coming from these fluorescent lights, but we don't see the light in the air, right? But we see it reflect off of things. And so we are able to see in this room because the light is bouncing off of the objects around us.
So when it's showing all this color, what is it bouncing off of? That allows us
So
to see?
in the rainbow, you mean? So in the rainbow happens when the sunlight hits raindrops in the air, and the raindrops act as little prisms. If you were to do this experiment, you wouldn't necessarily see this white beam of light, right? You shine the light here, and then you see this rainbow come out. That also happens by my front door. We happen to have a chandelier that's got some beveled glass on it, and when the sun hits it just right, it sends little rainbows all over the place, right? You see them on the walls. Now, in the sky, when there's a rainbow, what you're seeing is the light separated from the raindrops, and it's bouncing off the other raindrops. And so that's why you see it. This light, you would see the rainbow when it hits something, right? You would see it reflect off. And so it has to do with the water in the air. Yeah. Any other questions? Okay, so a laser dazzles the audience in a rock concert by emitting green light with a wavelength of 515 nanometers. Calculate the frequency of the light. Well, we had an equation that the frequency was equal to the speed of light divided by the wavelength. Well, the speed of light, 3.00 times 10 to the 8th meters per second. And they're telling us what the wavelength is, 515 nanometers. Are those units going to work out? No, they're not. So what I'm going to do is, instead of writing the prefix nano here, I'm going to write what it means. That's like a really fast way to do a conversion. Nano means 10 to the minus 9. So instead of the prefix, I'm going to write what it means. Now I've got meters on the top and meters on the bottom. So I'm going to have 3 times 10 to the 8th divided by 515 times 10 to the minus 9. And this is going to give me 5.83 times 10 to the 14. And the unit is per second. So that can be written as 1 over second, or second to the minus 1, or hertz.
How much is that?
That's a very high frequency. In 1 second, 5 times 10 to the 14th crests pass a point. We expect the frequency to be very high for visible light. Any questions?
Wait, sorry.
That's okay.
Back to that last slide. Is it 515 or 5.15?
That's a good question. This is 515 nanometers.
Okay, yeah,
So this is improper scientific notation. That's not the way we would report an answer. We would say 5.15 times 10 to the something, right? But just as a shortcut of unit conversion, your calculator will understand it.
For fiber optics, I think that it's like 800 and something nanometers. For fiber optic, for that networking.
Yeah, so a fiber optic, depending on the substance it's made of, will transmit
We can't see.
things of specific frequencies or wavelengths.
I don't think we can see that. No? See what? That 800 and something nanometers?
800
I think
nanometers?
it's 820.
No, I think it's very close. It's close to the visible. So any questions about this question? Any questions about the question? Well, visible light is really important to us, but it's actually a very, very small part of the entire electromagnetic spectrum. The shorter the wavelength, the more energy there is. Okay, so think of standing at the beach again. If the wavelengths are short, that means that the frequency is high. These waves are pounding you. That's more energy than if the wavelength is long. Another way I think of it, so if I look at this, and I look at this, which one looks more energetic? The bottom one. It's like this, right? Ah, more energy, and this is like, oh, this is like me getting out of bed this morning. I'm like, do I have to get up? Right? So long wavelength, low frequency, low energy. High frequency, short wavelength, high energy. You have to figure out how to remember that. So radio waves are at the low energy end of the electromagnetic spectrum, and gamma rays are at the high end. Stuff with high energy can damage biological molecules.
Or turn you into the Hulk.
It can turn you into the Hulk. Yeah, it'd probably just kill you or make you really, really sick. It's called ionizing radiation. It has enough energy that it can actually ionize atoms and molecules within your body. And as you can imagine, that's going to mess up your biochemistry. Yeah.
Is there any reason why gamma ray is the highest? Like, is there nothing that can go past it?
I don't think they know of anything that's past that. Yeah. Now, theoretically, could you have something higher energy in gamma rays? I mean, probably. Yeah, why would we expect that there be some end to it, right? I think it's more likely that we're just not able to generate rays like that. I'm not sure. It's a good question.
Would it be maybe once the wavelength reaches the Planck scale, the smallest thing it can be?
Yeah, if you think about energy becoming higher, you think, well, is there a limit on that? But energy becoming higher means that the wavelength is becoming shorter, right? And there must be some limit on how short the wavelength can be, because we're dealing with particles, ultimately. So, yeah, I like how you think. So,
Okay, when we're talking about wavelengths, what is doing the wavelength?
it's there's two waves, actually, perpendicular to each other. It's the electromagnetic, so electric field and magnetic field. And they are in sync with each other. So as the one's coming in and out, the other's going up and down at the same time. Yeah. The light stuff is a bit to get your mind around, but it's so much easier than the quantum mechanics. Okay, so this is a typical graphic that's shown illustrating different types of electromagnetic radiation. And there's two different scales here. There's frequency and there's wavelength. And here we see that the frequency is increasing, 10 to the 4th up to 10 to the 24th. And the wavelength is decreasing from 10 to the 5th down to 10 to the minus 15th. So this is a very small wavelength. This is a very large wavelength. These radio waves, some of them, the wavelength is like on the order of a mile long. That's really long. Do wavelengths damage your body? Nope.
No?
Not radio waves, no. There's radio waves in this room right now.
Wait a minute.
Because if you turned on a radio, could you get a signal in here? Yeah? There's radio waves. There's radio waves everywhere.
Well, hold on.
but they're very low energy.
How about the microwave? That's radio waves.
Microwaves are more energetic than radio waves. So here we have, so energy is going here from low to high as wavelength goes from long to short. So here we have, squeezed in the middle here is the visible. And what they've done here is they've blown up the visible part. So this is from 750 to 400 nanometers. And all of this fits in here between ultraviolet and infrared.
So it is not visible.
Microwaves are not visible.
No,
Radio waves are not visible.
But I asked a little while ago.
The 800, no, not quite. Not quite. 800 nanometers would be just below this. So not visible. So there's a section in your book, and they give information about this, and I want you to read about it. I'm not going to go over everything in lecture. I think it's a good idea to memorize this order. Radio waves, lowest energy, then microwave, then infrared, visible, ultraviolet, X-ray, and gamma rays. So ultraviolet is beyond violet, right? And infrared is below red. Infrared is heat, okay? Everything that is warm emits infrared radiation. We're all sitting here emitting infrared radiation. Microwaves, its placement here below, lower in energy than infrared, might be a little confusing because, well, how does a microwave cook your food and get it hot then? The frequency or the energy is lower than infrared, but it is at a wavelength that is very easily absorbed by water. Water is the key to using a microwave. If there's no water in the substance, it's not going to get hot. There are other substances that absorb as well, and that's why there are some plates that you don't want to use in the microwave because they'll get really, really hot, right? But water is what gets heated up. So the microwaves cause the water to heat up, and that heats up all the food around it.
I heard that they have now some grills, you know, where you grill meat that use infrared. I don't know if that's true.
Yeah, you can use infrared to heat things up, definitely. So the light, white light is, oh, question. Yeah, go ahead.
Like, just because we can't see things, like more colors, are there more colors? Like,
That's a good question. Just because we can't see colors, does that mean there aren't more colors? There are definitely, the color really is our brain's interpretation of the electromagnetic radiation. And there is a continuous spectrum of electromagnetic radiation. I think if you look at different species of living organisms, you'll find that some have different ranges of what they can see. Just like hearing, you know, dogs can hear higher pitches than we can hear. That's the idea of a dog whistle, right? That we can't hear, but the dog can. And so I think for seeing, yeah, you could see other wavelengths. It's interesting to think about, well, what color would that be, right? It's kind of mind-boggling. I don't know if I have a picture of the infrared. Oh, here it is. So infrared is the wavelengths that are just a little bit longer than visible. And so we can't see infrared radiation, but we can develop a sensor that can detect it, and we can make a camera. There's a thermal imaging. Right, so here's a picture of a guy with his dogs. And what we're seeing is not visible light reflecting off of them, but we're seeing the infrared radiation that is being given off by them. And so there you have proof dog's nose is cold. So blue is colder, and red is hotter, and yellow is in between. And so here we see the man's exposed skin, and that's giving off more infrared radiation. And here where the dog's fur is very thick, we see very little infrared radiation.
Why some spots that are white? Like
White, I'm not sure what that indicates. That it might be even hotter, I'm not
That's
sure.
what I was gonna say, that's just the color they chose to represent.
Right.
different ways, so that we could see it.
Yeah, so this,
They could have chose that red to be blue or that green to be whatever.
yeah, so this is not something that is actually being seen, but it's being measured, and it's being converted into colors so that we can look at it with our eyes. It's being mapped, basically.
Being like reference from like the light spectrum, like Roy G bit, how red is yellow.
They probably chose the colors in that way, and if you look at like not satellite images, but the radar for weather, you know, and they chose, okay, we're going to use the purple to be the worst, you know, most intense weather, and the green is going to be lighter, and there's a continuum, right? And so they chose what to identify it as. It's just like color coding, like drawing a map and you're color coding, well, these states are Republican and these are Democrat or whatever. They chose to do that. But we can't see this radiation with our eyes, but we can make a detector that can detect it. And this is the basis of night vision. So, you know, they're looking for somebody who's hiding in the woods. Well, you can use this infrared to see all the warm things in the woods. And it's like, yep, there's the guy right there. You can't see in the dark, but you can see the heat given off. Kind of neat. When we take, where did that come from? Didn't we already talk about that? Oh, this is the same picture, that's why. Okay. So we can separate light into the different colors. I don't know why that's in there. That's interesting, we talked about that. Okay, so waves can interact with each other. Now, one of the coolest things I remember from high school is in physics class we had these wave tanks. And they were clear bottomed, shallow, and above the desk, and they had a light source, and you could have these little wave generators, and then you could see the shadows underneath. It was really, really cool. You could actually see the constructive and destructive interference of water waves. So when the waves are in phase, meaning their peaks are lined up with each other and they interact, they constructively interact and they get larger. When they're out of phase, when a peak meets a trough, then they're going to cancel each other out. If you've ever played around on a trampoline, you may have experienced some of this. So if one person is bouncing and the other person bounces just right, they'll go much, much higher, right? Or you'll just like stop dead. Like, what the heck happened? It has to do with in phase and out of phase, constructive and destructive interference. So here are two waves that are in phase. Their peaks line up. And so when they interact, they add together and they get larger. Their speed is the same, their frequency, their wavelength is the same, but the amplitude changes. When we have waves that are out of phase, here we've got positive here and negative there. And when they interact, they can cancel each other out completely. And that's the idea of the noise-reducing headphones, the noise-canceling headphones, is that you take the noise coming in and you shift it in phase so that it's out of phase and you can cancel it out. So it generates a noise that cancels the noise coming in. Any questions about this? Another thing that waves do is they diffract. So traveling waves, when they encounter an obstacle or an opening in a barrier, they're going to bend around it. So waves do this, but traveling particles do not. Particles don't bend around obstacles. They either hit the obstacle or they go past the obstacle. It doesn't cause them to bend, but waves do. So we see diffraction of light through two slits. If the slits are separated by a distance that's on the order of the wavelength of the light, we get an interference pattern caused by the diffracted waves. And that interference pattern is a characteristic of all light waves. All light waves will do that. So here's an illustration of what this is talking about. So here's the wave, and what we're seeing here represented by these lines, those are the crests of the waves. So here's a crest, and there's a crest, and there's a crest, and there's. And so as this wave travels to this opening in the the opening in the barrier, and it hits this, as it goes through, it's going to curve and become diffracted. That's diffraction. Particles don't do that. Particles, here you're throwing particles at this hole. The ones that hit the hole go straight through. The ones that hit the barrier stop or bounce back, but they don't diffract. Yes?
Is that like how Wi-Fi works in an open house? Even though there's doors, it'll go through the gaps in the ground first?
Yes. And this is why radio waves can get into buildings and stuff, right? Some of it is some electromagnetic radiation can actually travel through walls and stuff, but diffraction is also a part of it, because sound travels by waves as well. In Reedley, the marching band comes out and tries to raise money by marching around, right, in the streets. And so you hear the marching band, and it's odd. You know, you may hear the bass sounds very, very clearly because those are a longer wavelength and they bend around buildings differently than the higher sounds. And so you hear different parts of them as they come closer. And it's not that the bass drum is close to you, it's that the sound is diffracting off the buildings differently. I'd like to be able to see all these things going on, but then that would probably be very, very confusing.
I installed wireless internet like out in the country where there's no DSL or
Mhm.
cable. And one time I went to do an installation, and there was this big old metal building
Mhm.
in front of where I was supposed to do it. And I said, this ain't gonna work.
Yeah, the metal building just stops it.
Yeah, but then I started moving the antenna, and I put it to a wall next to another building.
And then it was
and
fine.
Somehow I
Yeah.
just got
And
it
so
off
there's
of the wall.
these hot spots, not just that there's a generator there, but there's places that it works really well, and there's other places that are like really, really dead. And it just has to do with how everything is diffracting. And you can see the same thing with water waves. So I've got another video here, but I want to explain this first, and then we'll watch the video, and then I'll maybe explain it again. So here we have a light source sending out waves, and now we're hitting two slits instead of just one. As the waves hit the slit, they diffract. And these waves are going to be in phase because they came from the same source, right? As the diffracted waves spread out and run into each other, they create this diffraction pattern. So there are places where the waves are out of phase and we see a dark spot, and there are places where the waves are in phase and we see a light spot. And this is the diffraction of the light. So let's watch this video. Let me dim the lights.
What is light? What is light? What is light? That's a good question, isn't it? What is light?
Isn't it an element?
Light is brightness, I guess.
We have auras,
We all have auras.
which are light.
Yes, they are. It lights up the room. It makes it not dark.
What's the difference between blue light and red light?
The colour.
It goes through your eyes and then you see stuff.
They range from white to red to orange to green. It's like the chakras of your body.
Can you see my aura?
No, not particularly right now.
Is it too bright out?
It's very sunny out here today.
Does that make it harder to see someone's aura?
Not necessarily.
If I was to explain it to a blind person, right,
Yeah.
it would be the difference. You see nothing whatsoever as a blind person, whereas I see things in front of me.
To be fair, the question of what light is not an easy one. For centuries, the greatest minds in science debated this issue. In the late 1600s, Newton proposed that light was a stream of particles, or corpuscles. He proposed this in his treatise Optics. But at the same time, a Dutch physicist named Huygens proposed that light was a wave. And this debate raged on until it was settled by the experiment I've recreated today. Thomas Young's double-slit experiment. To make sure I got the experiment right, I went to the original source. With the help of Brady Heron, I managed to get into the vault underneath the Royal Society in London. There I found Thomas Young's handwritten notes from 1803.
I brought into the sunbeam a slip of a card, about 1/30th of an inch in breadth, and observed its shadow, either on the wall or on other cards held at different distances. Besides the fringes of colors on each side of the shadow itself was divided by similar parallel fringes of smaller dimensions. Wow.
This is an experiment so simple that you could make it at home, and yet so fiddly that I have never seen it before done with sunlight.
I was thinking about doing it in a box, like a fridge box.
And you can take it out on the street.
Taking it out on the street.
Could I possibly interview you guys for about a minute? We're doing a science experiment. I have here is an empty box. And this is a little eyepiece where we can look in, and this is a hole. And I'm going to place this slide above that hole. And if you look closely, you'll see that there's two openings. Very narrow openings side by side. It's a double slit. Now before we have a look, we need to tilt it towards the sun a little bit. So we want the sun to hit this double slit directly. What are we going to see on the bottom
Well,
of
the
the
obvious thing you think you're going to see is you're going to see two lines.
2 lines on the bottom of the box. 2 bright bands.
2 little lines.
think,
Yeah, I think it'll be one line instead of 2.
I could expect to see the whole box lit up.
It'll probably be a kaleidoscope of some sort.
A bunch of colors.
Probably, yeah.
Rainbow, different colors. There, have a look. You expected to see kind of one line. Is that what you see?
No. I see dots.
How many?
It's one circle.
Well, there's one in the middle strongest, 2 either side.
The 2 on the outside are multicolored. The one in the middle is just white.
And kind of a rainbow.
The rainbow colour as well. Quite a few colours and lots of little dots.
Like there are more dots appearing.
I think I can even see more dots spreading along. Yeah, that's amazing. Yeah, I can see tons of dots. Not tons, but I can see dots spreading across that way.
Either side.
Yeah, definitely.
Isn't that amazing?
Yeah, that's incredible. And that's just nothing else apart from
2 slits.
2 slits. That's incredible.
Well, all we're doing is we're putting a light through 2 very narrow slits side by side. How does this make any sense?
There's some kind of principle involved in it that the average person is not familiar with. That's the only explanation.
No, I'm really confused by it, but I'd like to find out why.
People were debating, is light a wave or is it made of particles?
So what causes that? Well, if light were behaving as particles, you would expect them to go through each slit and just produce a bright spot underneath. So we would see 2 bright spots on the bottom of the box. But if light's behaving as waves, then the wave from one slit can interact with the waves from the other slit. I've got a demonstration here on a little pond where we can see this with water waves. I have 2 sources of ripples, which are basically like the 2 slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the 2 sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference and there's basically no wave there. And this is exactly what was happening with the light. When the light from one slit met up peaks with peaks and troughs with troughs, they constructively interfered and produced a bright spot. But if the trough from the wave from one slit met up with the peak of the wave from the other slit, they would destructively interfere and you wouldn't see any light there. It's light canceling itself out.
It's basically the same as like having 2 drops of water fall in a swimming pool.
That's right.
Exactly the same
And then they go
pattern.
and overlap. As this ripple overlaps with those ripples,
Yeah.
down the bottom, you get a series of, you get like a bright spot, and then a dark spot, and then a bright spot, then a dark spot, then a bright spot.
Now there's a slight complication, which is that sunlight is composed of many different colors, and they have different wavelengths. So obviously they're going to meet up at slightly different points. And that's what caused the rainbowing effects as we go further from the central maximum. You saw the ones to the right were slightly colored.
Yeah,
that's
it's
because
bugging
the
you.
reds are going to meet up at different places than the blues.
And that's all that makes the colour differences in different wavelengths.
Exactly.
That's amazing.
So the difference
So
between
there's
red
still
and blue...
that red bin over there, and the green part is just, I'm seeing
It's a
that, and it's
different-
just different
different length.
wavelength. And that's how we bring in all these beautiful colours all around us.
Exactly.
That's amazing. I'm amazed. Oh, good on you, thanks, Ben.
Thank you.
I have been enlightened, literally.
I love that video. So this is what he was doing on the lake, right? So he's making 2 sources. This would be the one ball going up and down. Here's the other ball going up and down. And he's making these ripples. And as they travel out, they overlap constructively and destructively. And then the slit, the light, we see the different bright and dark spots. And the colors are because of the wavelength differences. The red overlaps at different places than the blue. Yes?
So would it be both constructive and destructive at the same time?
It can't be constructive and destructive at the same time.
So what would make it destructive?
Well, what makes it destructive is when the waves get out of phase. And when they're in phase, they are going to be constructively interfering. And the reason that we have constructive, sorry, I lost my pointer. The reason we have this alternation here is because the distance traveled by the waves causes them to be in phase or out of phase. Any questions?
So it's like when you put 2 batteries in series.
A little bit, yeah. If you put 2 batteries in series, they're both hooked up in the same direction, you get more power. And if you put them in backwards, you get none.
0.
They're going to fry each other out. Yeah. So that's how waves behave, right? And particles, I think we understand, throwing particles at a hole, some are going to go straight through and some are just going to be blocked, but we're not going to see this rainbow effect. We're not going to see these different spots. We're just going to have 2 bright lines. So it was observed that many metals will emit electrons when a light shines on their surface. It's called the photoelectric effect. And classic wave theory explains this by saying, well, the energy from the light is transferred to the electron, and the electron gets enough light, enough energy from it, and then it has enough energy to come off of the metal. So according to this, only the amplitude of the light would affect the emission of electrons. A brighter light would cause you to emit electrons, and a dimmer light would not. The wavelength shouldn't have anything to do with it. So if you had a dim light, the electrons would absorb the energy, but it would take a while before they would get emitted, before they could soak up enough, store up enough. Does that make sense? So, this was the idea. So here's our metal surface inside of this evacuated chamber, because without the vacuum, you can't measure the electrons being given off. So we've got a battery hooked up here so to make this a positive electrode to attract the electrons that are being emitted. And this allows us to just detect, okay, some electrons are coming off, or no electrons are coming off. So we've got light hitting this metal surface, and if the meter moves, then we know that there are electrons being given off. So this is what actually was observed. So if we increase the frequency of the light, we start with a low frequency, no electrons were ejected. You could wait all day long, nothing happens. You get to a certain point and electrons start being emitted. If you have low intensity, you would get a particular level, and if you had high intensity, you get a higher level. But as you increase the frequency of the light, that didn't affect how much was being emitted. It had to do with the frequency of the light. And there was no lag time involved.
Oh, so does that answer the question that why the red bounces off and not the other ones? At a different frequency?
Well, it definitely does have to do with the frequency. And so some things will absorb the light energy, and you can, I mean, when you go outside and the light hits your skin, it feels warm, doesn't it?
Yes.
Right? And black things are going to get hotter than white things. That's why people in the valley tend to favor light-colored vehicles, right? Because they don't get as hot as a black car. Why is that? Well, white objects are reflecting more of the light, and black objects are absorbing it. When they absorb the light, they absorb the energy of the light, and they get warmer. So what we observed here is that difference in intensity of the light did affect the rate of electron ejection, but there wasn't any lag time at all. But it did have to do with the frequency. And so Einstein explained this by proposing that light energy is delivered to the atoms in little individual packets. They're called photons or quantums. So a photon is a packet of energy, a piece of light, a piece of energy. The energy of that photon, that packet, is directly proportional to its frequency and inversely proportional to its wavelength. That proportionality constant has a name. It's Planck's constant, and it has this value. So the energy of a photon equals Planck's constant times the frequency. Or it is equal to Planck's constant times c over lambda. Because remember, we learned earlier that the frequency is equal to c over lambda. So these are just saying the same thing. But the energy is related to the frequency of the light. So let's do an example calculating something like this. A 100-watt light bulb radiates energy at a rate of 100 joules per second. And just parenthetically here, the watt is a unit of power. Power is energy over time. So a watt is defined as a joule second. If all the light emitted has a wavelength of 525 nanometers, how many photons are emitted per second? And it says assume 3 significant figures. This 100-watt looks like 1 sig fig to chemists, but it's intended to be 3. Does this seem like a very strange problem? Like, what the heck am I supposed to do with this, right? You don't throw your hands up when you read something like this. You say, I can do this. I'm just going to identify the pieces. I'm going to figure out what I can and deal with it. So 100-watt light bulb is radiating energy at a rate of 100 joules per second. Okay, well, let's write this down. Writing stuff down is a good idea. 100 joules per second. The light being emitted has a wavelength. Oh, we know what that is. Lambda equals 525 nanometers. How many photons are emitted per second? Well, we just learned about an equation that relates frequency to energy or wavelength to energy. E equals hc over lambda. I don't remember, it's 6 point something. 6.626 times 10 to the minus 34 joule seconds. 6.626. Oops, that's not what I wanted to do. H equals 6.626 times 10 to the minus 34 joules times seconds. Well, we have a wavelength, and we know what Planck's constant is. We know what the speed of light is. Could we calculate energy? Yeah, we could just put these things together. Let's do that. Energy, hc over lambda, where h is 6.626 times 10 to the minus 34 joule seconds. C is 3.00 times 10 to the 8th meters per second. And the lambda, 525 nanometers, I'm going to pull that trick again, and instead of writing nano, I'm going to write what it means. And then let's check our units here. Here I've got per second and second. Those cancel out, and the meters cancel out, and so I'm going to end up with joules. 6.626 times 10 to the minus 34 times 3 times 10 to the 8th divided by 525 times 10 to the minus 9. So this is 3.7. We were told to use 3 sig figs. 7863 times 10 to the minus 19 joules. So we say, oh, okay, I calculated something. But I'm supposed to calculate how many photons emitted per second. This energy I just calculated, that's the energy of what? What's it? No, it's the energy of one photon of light. So a photon is a packet of light, a piece of light. It's like, I'll have 2 pieces of milk, please. What? Yeah, light comes in pieces. So this is the energy of the photon. It's based on the speed and its frequency. So this is the energy of that light. That's 1 photon. Well, if the light bulb is giving off 100 joules every second, how many of these are coming off in 1 second? So this is equal to 1 photon.
So is that times 100?
Well, is that times 100? Let's just wait and see here, okay? So I have 1 second. That's my time period. And I have 100 joules per second. I should keep this, well, start over. Let's try to be consistent in our units. 1 second times 100 joules every second. So the seconds cancel. And then I have calculated a conversion factor here. 1 photon is this many joules. So if I put joules in the bottom and photon on the top, then my units are going to work out so that I get a number of photons. So 1 photon is 3.7863 times 10 to the minus 19 joules. So I have 1 times 100 divided by 3.7863 times 10 to the minus 19. And that's going to give me 2.64 times 10 to the 20th photons. That's a really big number. Is that reasonable? Should we? Is a big number like that okay?
Yeah.
It is. Because a piece of light is really small. Yes?
If we're finding how many photons per second in our units, just collectors of photons, and not photons per second, we just assume that.
Okay, so we're supposed to find how many photons per second. So the way that makes sense to me is to say, well, per second, so how many photons in 1 second, right? So that's why I started here with 1 second. And then I found the number of photons that would be emitted in 1 second. So that would be that many photons per second. Problems like these, you really have to be able to look at the units, and the units are going to help you figure out what to do. Any questions? Let's see.
I have a question.
Uh-huh.
Einstein's constant, do we have to memorize that, or is that going to be given to us?
Planck's constant. You don't necessarily have to memorize that. No, I'll give that to you. Okay, I thought... Oh, yeah, we're going to get to that later. This section just goes on and on forever. Okay, so we did that one. Arrange these 3 colors of visible light, green, red, and blue, in order of increasing wavelength. Now, this is a very common way to ask questions like on an exam. So, in order of increasing, that means that they want you to list the smallest first, and then the middle, and then the biggest. Because as you go from left to right, like we read, it goes from smallest to largest. And I'm surprised always, every semester, by the number of students who do it exactly backwards. They didn't understand the question. So, wavelength. We've got wavelength, we've got frequency, we've got energy per photon. I wouldn't necessarily answer these 3 questions in the same order. So, red, green, and blue. So if I couldn't look at the table, that graphic of the thing, how could I answer this? Okay, so this is what I'm doing in my head. I'm thinking, okay, here's the spectrum, right? And I remember that over here this was low energy, and I had visible light in the middle, and this was like radio waves and stuff. And then over here, this was high energy. And then I had the colors in here. This was infrared, so that tells me that this is the red light at this end. And this was ultraviolet, which means that the violet, oh, what happened to my violet, is at that end. Okay, does that make sense? Higher energy going up this way. Does ultraviolet hurt you? Yeah, sunburn, right? Can ultimately give you skin cancer. Infrared, that's heat. Now, too much infrared can hurt you too, but that's heat, right? That's lower in energy. So ultraviolet. So these names, ultraviolet and infrared, help me to remember the direction of the Roy G. Biv. Does it start at the left or does it start at the right? So this is red and this is violet. So in here, I remember Roy G. Biv, and so I've got red, and then I've got green, and then I've got blue in here. So the answer to these, there's really only 2 choices for each of them. It's red, green, blue, or blue, green, red. Has to be one or the other. So energy per photon, the way I drew this out is low energy to high energy. So the amount of energy per photon is going to be lowest for red, intermediate for green, and higher for blue. So I would say red, green, blue. Does that make sense? So then I have to decide, okay, there's frequency and there's wavelength, and there's some things that are backwards, right? Upside down, inversely proportional. Okay, so I'm going to think about waves again. High energy. High energy is waves going bang, 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 right? So that's high energy, and this is low energy. So short wavelength, so this is high energy, low energy. So if it was high in energy, it's got a short wavelength. So for the wavelength, the order is reversed. Blue is the short wavelength, green is longer, and red is the longest wavelength. And then frequency. Which is higher frequency? This is higher frequency, right? High frequency, high energy, those go together. So the answer to the energy question is, or the frequency is going to be the same as the energy.
And I'm going to get it wrong.
So these are the sorts of questions that can be really challenging to think about on an exam. And just flat out memorizing stuff, I don't think is a good strategy. I'm not good at memorizing random stuff. But if I can think about it and make associations with things that I know, like being bombarded by ocean waves or something, then I can reason it out on an exam. Any questions? Yes?
Why are cool colors called cool colors if they're hotter than warm colors?
That's a good question. Why are cool colors called cool colors? So we think of like blue and violet and green as being cool colors and red as being hot. Which is closer to IR, infrared? The red. I'm guessing, I'm making this up right now. I'm guessing that's why.
Okay.
Because infrared is heat. If you've ever been, like, well, maybe some of you have infrared lamps in your bathroom, but, you go to a nice hotel and they've got this, you flip on the switch and you're like, did anything happen? Oh, there's this weird reddish glow up there. It's an infrared lamp. It doesn't give out much light, but it gives out heat, and it warms the bathroom up for you, right? And so red light is going to be closer to that heat radiation than green or violet. Any other questions? Ejected electrons. So back to that idea of the photoelectric effect. How can a photon of light eject an electron? Well, the photon has to have just enough energy to dislodge a single electron. Well, why don't the electrons just fly off all by themselves? Because they're stuck, right? They have a binding energy. So, is this phi? Greek letter phi? Is that phi? Anybody know? Phi? Phi, phi, phophon, something. That Greek letter is used to represent the binding energy of electrons. So if we irradiate this metal with a higher frequency, the electron's going to absorb more energy than is necessary to escape, but it's still going to escape. What happens to the extra energy? Well, it becomes kinetic energy of the ejected electron. So the kinetic energy of that electron that's getting ejected is going to equal the energy of the photon minus the energy that was binding it. So this is a little bit like perhaps going to Disneyland, and you've got $300 in your pocket, right? You go to Disneyland, you have to pay to get in, right? So you pay the entrance fee. That's like this binding energy. This gets the electron through Disneyland gates. You get into the park. Here it's leaving the metal. What happens to the extra money? Well, you have that available to buy stuff at Disneyland, right? So it's the total amount of energy minus what it took to kick the electron off. The rest of the energy is kinetic energy of the photon. It's going to, not the photon, the electron. So the electron's going to be moving faster if there was more energy. So the energy of the photon is h nu, and phi is the energy that was binding the electron to the metal. So let's look at this. Suppose we had a metal, and we can eject electrons from it by shooting yellow light at it. What would happen if we struck it with ultraviolet light? You're too fast.
More energy, no?
Okay, so high energy,